Inequality. That's the difference, okay? The open circle or the dotted line means you can't actually get to those points. You get right up to them. But the solid line or the solid circle means you can. So these points will work in that inequality. How many points are we talking about today? Good for you. So when we're doing our graphing linear inequalities, our first idea is, well, we want to make sure we temporarily set this thing equal to 0. That way we can find our x and y intercepts and graph at least the line part of it. However, we know that we're not just graphing lines here, we're actually shading the half plane. So it's either going to be shaded at the top half or the bottom half of our graph, and that's telling us our whole solution set. So the first thing we're going to do, let's set this thing equal to 0 temporarily. By the way, do we ever do this any other time besides right here? The only time you're ever going to switch an inequality to an equal sign is right here. We'll do our 3x plus 2y equals 12 just for a second, and this is just so that we can find our x and y intercepts. Ladies and gentlemen, in order to find the x-intercept, what do I do? Good. Okay, so if I want the x's, I better cover up everything except the x's. That makes sense. So that's gone. I'm just going to rewrite what's left. So x-intercept, we cover that up, we write what's left over. That's 3x equals 12. And there's at most one step. There's at most one step after covering up in order for you to find the intercept. In our case, what is that step? Yeah, we'll do that. Divide both sides by 3. And all of a sudden we have our x-intercept, and that's 4. Not so bad. So here's our x, here's our y. Here's what we know already. If we just found our x-intercept, we just found where our graph is going to cross the x-axis. That's this one. Where's it going to cross the x-axis? Yeah, it tells us. So we're going to go over to 4. And we'll put a 1 right there. That's how you use your x-intercept. You just put it on the x-axis. That's half of your graph right there. You only need 2 points, right? We already have 1. Now, let's go ahead and find the y-intercept. What did we do in order to find the y-intercept? Good, and setting x equals 0 means we're just going to cover that up. If we want the y-intercept, let's cover up everything except the y. One thing on this, make sure if you're going to cover up everything except the y, I know that's a plus sign, it really doesn't matter in this instance, but don't cover up the sign, because if that was a minus, that would change our problem we saw last time. You with me on that? So cover up just the x term and write what's left over. So we have a 2y equals 12. We'll do the same process we did for the x-intercept. That's just divide both sides by 2. We get y equals 6. If y equals 6, that means, well, are we going to go up or down on the y-axis? Good. Put a point there. Hey, you only need 2 points to graph a line, right? So we've got 2 points. Let's graph our line. This way's harder. This way, harder. I don't know why. The other ones this way look good, look great. Those ones have a little kink to it. Wait, what now? Why? Okay, so why is this not right? What would solid represent? Yeah, the solid would represent equal to, because it would mean that the line is actually included in our solution set. It means that we can go up to the line and actually include the line. If we're not equal to, it means the line itself is actually not included. We go all the way up to the line, but the line itself is not in our solution set. So in order to represent that, if we do not have equals, remember, we're not looking here, right? That was just a temporary step, just for like 5 seconds, so you could write your x and y intercept. We don't ever use that again. We look back up here that says it's not equal to, so I definitely need a dashed line or a dotted line. Either one. And we're done, right? Why are we not done? Okay, we have to check 1 point because, yes, we have to shade it. We've got to shade half of this graph. Either the top half, we'll call this the top half. Either the top half is going to be shaded, representing all these points, or the bottom half is going to be shaded, representing all those points. One of those halves is going to work. What point do we always like to check, ladies and gentlemen? Okay, can we check 0, 0 here?
Yes.
Yeah, absolutely. As long as it's not actually on the line, you can check it. So we're going to write down here to check. we're checking. In this case, of course, we're checking 0, 0. Now, where do you check 0, 0? Do you check it in your original inequality, or do you check it in this equation? What do you think? Yeah, this was just for a second. We're using that one. So check that point. We have 3 times 0 plus 2 times 0 is greater than 12. It's nice because this right here, this makes one whole side of our inequality equals 0. That's why we use that point if we can. 0 is greater than 12. What do you think? True or false? Definitely false. Well, here's what that said. If we checked 0, 0 and it was false, did that point work in our inequality? Are any of these points going to work in our inequality? Okay, so are we going to shade, let's call this the bottom, are we going to shade the bottom half or are we going to shade the top half? If this point doesn't work, none of these work, all of these work. We shade that. Go ahead and give that a try with that example. So I want you to temporarily set that equal to 0, equal instead of inequality. I want you to find your x and y intercepts, graph them on an xy axis, use the appropriate type of line. Check your point shape. That's the whole process. Good, that's a good work so far. So see x and y intercepts, see the appropriate type of line, and some good shading. We're going to start up here just a bit. Okay, so the first thing I hope you did was temporarily change that inequality into an equal sign. What that lets you do, only for one reason, we're just finding x and y intercepts with that. So we'll say 3x minus 6y equals 12 just for a second. We'll cover up some appropriate things to find the appropriate intercepts here. So if we want to find the x-intercept, which we'll do first, we're going to cover up the y term. That means we're plugging in y equals 0. That's really what we're doing. We're just going to write the rest. By the way, would this still work if that number wasn't divisible by 3? What if that was like a 16? Is that going to be okay? You just have 16 thirds, that's going to be 5 1/3. You can still graph that on a graph. That'd be okay. So we divide both sides by 3, and we get x equals 4 again. Now for our y-intercept, same idea. We still want to set our x equal to 0 this time, and we cover up our x term, not with the negative covered up, without the negative covered up, because this sign goes with this term. So we're going to cover this up and do negative 6y. Look at that. And we've got your intercepts of 4 and negative 2. Good. That's fantastic. And we can start graphing this. So we know we crossed the x-axis at 4. We know we crossed the y-axis at negative 2. Our line's going to intersect with both those points. Do I need to make that a dashed line, or do I leave it solid in this case? Good, that's worth a couple points in your test. You know that that's a solid line versus a dashed line. It's pretty easy to tell, right? Just go right up here. If it's equals, keep it solid. If it's not, make it dashed. We check 1 point. If it's not on the line, we're going to check 0, 0. It's the easiest one to check. So over here, we put check 0, 0. And what we're doing is essentially plugging in 0, 0 for our x and our y coordinates. So, let's see. True or false? Definitely true. If it's true, you shade the sides, the point you just checked is on. You shade that half point. So 0, 0 work, it represents all these points work. So we're going to shade this entire half point. Did you raise your hand feel okay with these two examples? Cool. Now let's look at what happens in something like this. This doesn't look a whole lot like these examples. You with me on that? Can we do the same thing that we did over here? Well, first thing, if you're going to try to do this, you're going to have to get it in the correct form. How can I get it in the correct form to use this? I could subtract y and get 0, or I could subtract 3x from both sides. Either way would work, okay? Let's subtract 3x. Don't write this down. I want you to see something. Right? Don't write this down yet. I want you to see something. If I subtract 3x, I get negative 3x plus y is less than 0. I'm writing it that way because that's standard form. Do you guys see the standard form? Now, let's try to do this method with that problem. You ready for it? Here's what you do, right? You write x-intercept. You write y-intercept. In order to get the x-intercept, you would cover up the y. Well, you set equal, right, firstly. You cover up the y and you get negative 3x equals 0. True? And you would get x equals how much? Definitely, divide by 3, negative 3. Is 0. But then in order to get the y-intercept, you'd cover up the whole x term, wouldn't you? And you go, oh, okay. Y equals 0. Wait a minute. Wait, hang on. Let's grab our intercepts. X equals 0. You know where x equals 0 is? You know where y equals 0 is? Uh-oh. How many points do I have? How many points do you need to graph a line? Can you just go, oh, there's 1 point. I know it looks like this. No, we can't do that, right? Because there's an infinite number of possible lines you can go through that. We have no idea how that looks. This one's not going to look like that. In fact, this one's going to look much steeper than that. This is a slope of 3/1. So you're not going to have that look of a line. So what I'm trying to tell you here is that this method works great if you have a number here and here. However, there's certain cases where you cannot use this cover-up method that I taught you, the standard form version of graphing a line. Are you with me on this? You can't do that. So write this down. You can write this example if you'd like, but make sure you write this down. If you have ax plus by less than, greater than, less or equal to, greater than, equal to, whatever the inequality is, and a 0 over there, you cannot use the standard form version of graphing a line, because look what happens, folks. If you cover this up, you get 0. If you cover that up, you get 0, right? That means you get the same point twice. There's no way to graph a line with the same point twice. You can't do that. If you have this, you must use slope intercept. Only other way we got. So here, this whole issue, if you don't have, can you see it right away, by the way? Look at the board here with me. Can you see it right away that you have no constant term over here? There's no constant. Here there's a constant, here there's a constant. That means you can do it. Over here, when you don't have a constant, all of this nonsense is not going to work because of this reason. Because of that reason right there. You have the same point twice. That's not going to happen. Okay, so if this doesn't work, if that doesn't work, we have to use the slope-intercept form of the line. But check it out. That's already in slope-intercept form, isn't it? Why? Well, we're going to make it equals. But let's temporarily make it equals. I'll write this problem right here. Y is less than 3x. But if we don't have a constant term, leave it in y-intercept or make it y-intercept. We're going to set this equal to y equals 3x. We're going to make that y equals 3x. Hey, can you graph y equals 3x? Let's see, what's your intercept there? 0. Y 0. Do you guys see there's no constant, right? That inherently means that you're crossing at the origin. Not sure if you're with me on that. So we have the same situation, right? We know it intersects 0. If you would have done this, you would have seen that. So since we have no intercept, we already know we're still at that point for sure. We're still there. What's your slope? 3 over 1. What does 3 over 1 tell you? Are you going to go up or are you going to go down? Up how many? And over to the how many? So what this says is from this point. Do you see where I'm getting this point, by the way? You sure you're okay with that one? Because some people are like, I don't know where it's coming from. Where this is coming from is because we don't have a constant. It's plus 0. This is of that form, right? This is crossing at 0, right there. 0. The b is 0. And then we're going to use our slope, which is 3 over 1. To go up 3 because it's positive, over the right because it's over 1. It's 3 over 1. Graph our line. It's certainly not a 45-degree angle. It's much steeper than that. So we would have had the wrong idea if we just guessed at this. And graph our line. I need a show of hands to see if you're okay. I'm just graphing this at least. Guys up here? Yes? Guys on the right-hand side? Okay. Is this supposed to be solid or dotted? Good. Why? Yeah, we look right here, or the original. Okay, so we got that far, but now I have to shade it. Can I use the point 0, 0? No. If you plug that in, it's not going to work, first of all, but then it doesn't even tell you what side it's going to, we need to shade. So if you can't check 0, 0, you can check almost any other point that you want as long as it's not on a line. If you can't use 0, 0, I'm going to pick like 0, 1. That's the one I always go with, is 0, 1. If 0, 0 doesn't work, 0, 1 will work. Unless you have a vertical line at the y-axis, but that's generally not going to happen. Check 0, 1. Identify where 0, 1 is. Look at the board with me, please, real quick. 0, 1. Is this 0, 1 right there? Is this 0, 1 right there? Yes, that's 0, 1. So don't get those confused, right? Because if you mark down the wrong point, you're going to shade the wrong side of the line. So if I'm using 0, 1, I need to make sure. I'm checking that point right there. That's the one I'm looking at. What's my x coordinate? The 0 or the 1 here, folks? So I'm going to plug in 0 for the x, and what am I going to plug in for the y? So y is less than 3x. I use this, and I go, okay, y is 1, that's 1, less than 3 times 0, x is 0. So I get 1 is less than 0. 3 times 0 is 0. Is 1 less than 0? Is that a true statement or a false statement? False. Here's what we did. We checked this point right here, 0, 1, because we couldn't check 0, 0. 0, 0 is on the line. Can't check that. We checked 0, 1. 0 for x. 1 for y. That fills out our inequality for us. We make sure we check this down, see if it's true or false. 1 is less than 0. 1 is not less than 0. That means it's a false statement. So here's what happened. We checked this point, and it was false. Are we going to shade the top side or the bottom side? And that's a perfectly fine looking graph. Would you raise your hand if you're okay with that one? Good. Let's try one more of these really to get the hang of this, and then continue. That was such a good example. Things are raining from the heavens. Did you see that? See? That had no help. Can't believe I just referred to this college's ceilings as the heavens. That's not my idea. Okay, anyway. X greater than 3y. X greater than 3y. First thing. Do you think I'm going to be able to use the cover-up method
Você quer? Só dois X.
In this example, what do you think? Do I have a constant term? So even if I were to get this all to one side, check this out. Even if I were to subtract 3y, I would get x minus 3y is greater than what? That means if I cover up two things, I would get 0 in both of them. This is telling me right here, I hope you listen to this, this is telling me that this line is going to go through the origin. Nod your head if you're with me. For sure. Because both intercepts are 0. I mean, you're going to go through the origin at some point. So if this is not, oh my gosh, if this isn't the intercept method, what are we going to do? Slope intercept. So we're going to temporarily set this equal to 0. Oh, sorry, set the inequality to equal sign. And somehow manipulate that until you get slope intercept form. Is this in slope intercept form? No. I need a y by itself in order to get slope intercept form. How do I do that? Okay, well, I could change sides first of all, right? Maybe change sides. So instead of x equals 3y, I get 3y equals x. We like to see the y on the left-hand side for some reason. It looks more natural to us. But now I don't want a 3y, I want a y. How do I get rid of 3? If I divide, please watch up here for a second. This side is going to be y. Are you with me on that? Right-hand side is x over 3. You can always write x over 3 as 1/3 x. You can always do that. X over 3 is 1/3 times x. Do you see why? If you don't see why, think of this as 1 over 3 times x over 1. If you multiply those, you're going to get x over 3, right? We're just breaking it up. Hey, is that slope-intercept form? Oh yeah, we can do that. So what's our y-intercept? I need y'all to participate on this. What's your y-intercept here? Sure, there's no number over here. Hey, that's why we did this in the first place, right? There's no constant, meaning I'm going to cross at 0. So on my xy axis, I knew initially I'm crossing at 0, but this proves it. I have no number after that x. That means our intercept, our b, is 0. We're crossing at the origin. What is my slope, everybody? 1/3. Am I going to go up or down? How much? And then over to the
Right.
how much? No tables, right? No tables. From our origin, because we plotted 0 here, because our b was 0, we're going to go up 1. We're going to go over 3. And we're going to put a point there. Up 1, over 3. Let's draw our line. Leave it solid, make it dashed. Which one? Definitely dashed. We have to also check a point. Because we need to shade this thing. Are we going to check 0, 0? Hey, look at that. Are we going to check 0, 0? We can't. It's going right through there. We can't check that point. What point are we going to check, maybe? Yes, I don't care what point you pick. But be consistent about it. That way you're not just messing with, getting all these different points up there. Be consistent. Check 1 of 2 points. Check 0, 0 if you can. If you can't check 0, 0, pick another one that you always check. Okay? Don't make it something like 1, 1. Make it something with a 0 in it. Because if the origin doesn't work, either the point right above it, that one's probably going to work almost all the time. Unless you have a vertical line right here that's going to happen. Pick that point. Pick like 0, 1 or 0, 2 or something like that. I always pick 0, 1. 0 for x, 1 for y means that in my original inequality, I'm going to have 0 is greater than 3 times 1, or 0 is greater than 3. Is 0 greater than 3? Is that a true statement or false statement? Definitely false. Am I going to shade the top half of the line, or am I going to shade the bottom half of the line? Definitely. I checked 0, 1. That's the point I checked. It was false. That's all false. This is all true. So that's how we graph those things. Ladies and gentlemen, do you feel okay with this so far? Okay, now I need to show you one more. You will get some of these on your homework. For some reason, people have a hard time with the next couple examples, so I hope that if you have questions on this, you ask me right now. Because they forget that we can actually graph constants on an XY axis, but they forget how. So let me just refresh your memory on how you graph something like x is greater than 3 if I want to graph this on an XY plane. If I want to graph this on an XY plane, the way we do this first, we can deal with the same idea, right? Set it temporarily equal to 0 to get your intercept. You could do that. I keep saying equal to 0. What I mean is set the inequality as an equal sign. Sorry for my misspeak there. What I mean is set that equal to the number instead of unequal to the number. X equals 3 is a constant line. What you can know is whether it's a vertical line or a horizontal line. What do you think it is? And if you really think about this, x equals 3, just like over, well, not there, just like the previous ones we did where we did the cover-up method, you would get x equals the number is your x-intercept, right? You go, oh, okay, 1, 2, 3, we put our x-intercept. Is there any y? So does it have a y-intercept? Clearly not. We don't even have a y. How can you make a line through that point that does not have a y-intercept? Can it look like this? If you know what a lot of people doing. They go, oh, x equals 3. I'm going to put at x equals 3. I'm going to draw a horizontal line. Well, I'll tell you what, if you do that every time, then all of your lines will be exactly the same for x equals 3 and 4 and 5 and 6, right? That can't be right. Be the same line all the time. Doesn't make sense. If we have an x-intercept and no y-intercept, the only way we can have it is a perfectly vertical line. Is it a perfectly vertical solid line or a perfectly vertical dashed line? Now here's what's cool. This is kind of neat. Remember on a number line, how the arrow told you which way to graph? Remember that? Well, this is basically just graphing on one of our number lines. Notice how it's not even really touching the y-axis. We can use the same idea. This says we're looking for x's that are bigger than 3. Which way is bigger than 3? Left or right?
Right.
Hopefully we get this right. Bigger than 3 is to the left or to the right?
Right.
Right. Shape that side. I can prove it to you with the check if you really want. If you check 0, 0, if you check 0, 0, you'd have 0 is greater than 3, right? Is that true or false? Is 0 bigger than 3? That would be false. This side would not be shaded, that side would be shaded. Same idea. You with me on this, folks? Okay, let's try one more. Let's do a y one. Let's do y is less than or equal to 2. Well, we do y temporarily equals 2. Y temporarily equals 2, ladies and gentlemen. Y temporarily y temporarily equals 2. Is that the y-intercept? Sure, where? Clearly, yeah, it says y equals 2. We're going to go right up there, the 2. Does it have an x-intercept?
No.
So this is represented by a horizontal or a vertical line? Definitely horizontal. Is it solid like I'm showing you, or is it dashed? Solid. Now, we're looking for y's less than or equal to 2. Y's less than or equal to 2. Where are the y's less than or equal to 2? Are they above or below my purple line here? They're below, yeah. The less than 2s, that's down here. This is 1, 0, -1. That's all these, right? So if you kind of go like this, actually this way, sorry. If you go like this way, I'll set it over here. That's like a number line. Positive 1, 2, 3, 4, 5, negative, -1, -2, -3. Less than 2 would be that way. And so you have easy. I mean, you can tilt your paper. I do this. I'm going to develop like arthritis in my neck from doing that. But it's all of this stuff. And if you check 0, 0, you get the same exact answer. 0 is less than 2? Yes, 0 is less than 2. Shade that side. Raise your hand if you're okay graphing these single linear inequalities. Now, what we have, here on out, what if we had not just one at a time, but 2 at a time? We're going to graph some systems of linear inequalities. And this is where it gets fun. You guys ready? Fun stuff here. Are there any questions before I go on? So let's look at systems of inequalities. I'll tell you what. The first part of this looks very similar to a piecewise function. It is not a piecewise function. There are 2 different functions that we're graphing at the same time. So I know it's a little confusing because I'm going to use the same bracket here, but please refresh your memory on piecewise functions when you get home today so you know the difference between them. On your test, which is on Monday, you will have both piecewise functions and systems of inequalities. You need to know the difference. So check that out. So a system of inequalities says, not only am I going to graph one of these on a graph, I'm going to look at 2 of them. That's why we have that bracket again. All that bracket means is look at these things together. Make sure they're on the same graph. If you have an f of x up front with some directions over here, that means it's piecewise. You only graph little pieces of it. If there's no f of x or g of x and there's no directions past my functions, that means you're talking, and there's inequalities, that means you're talking about inequalities. Okay? The piecewise functions won't have inequalities. The inequalities, well, they're going to have inequalities. Hey, before I go any further, how many people could graph this? Just ignore this for a second. How many people could graph that on my XY axis? Raise your hand if you could. Oh, I hope you can. Can't you? Can you graph that? Would the cover-up method work here? Sure. So can you graph it?
Yes.
And could you shade it? Sure, you can graph that one, right? Okay. Now all I'm asking you to do is graph that one and then do it again. Ignore this one now. Could you graph that one on your XY axis? Would the cover-up method work here? Sure, there's no zero there. That's great. So our cover-up method will work for both of those. We'll graph those, we'll still shade them. So our steps here are this. You're going to graph each of the inequalities just like you did before, including the shading. Now, you have to be with me on that. Just like you did before, including the shading. Graph each inequality, including shading. Step 2 is really not a step at all. In fact, I've taught you how to do this already. I mean, we know how to graph each of these individually, so it's not like we're doing anything new. We're just doing two of them at the same time. You with me, folks? But we also need to identify the solution set. Here's the idea. I want you to picture in your head what this would look like. Unless these lines are parallel, which they're not, this line is going to be looking something like this, right? And you're going to shade either the top half plane or the bottom half plane. You with me? And this line is going to be looking something like this. They're going to cross somewhere. Do you get it? And you're going to shade either the top half or the bottom half of this. Can you see that this shading is going to overlap in some region? It's not going to overlap. Maybe it doesn't overlap here or down here, but it might overlap here. That would be your solution set. Wherever you have the double shading, where the shading overlaps, that's your solutions. Those are the numbers, and here's what this represents. Those are the numbers that will work both in this inequality and this inequality at the same time. Remember the overlap that we did this? Remember that on your number lines? And you said, oh, there's those and, because they worked in both of them. Same idea. Same overlap here. You're overlapping the shading now. So you're going to get those numbers, those points, which work in both at the same time. So where the shading overlaps is your solution set. Let's do a few of these. These actually go pretty quickly once we know how to graph those, which we do. Let's see about this. Let's call this one number 1, and this one number 2, and let's look at 1 first. With inequality number 1, just focus on that like if it was a problem all by itself. First thing you do, what would you do? The first thing you do when you're graphing linear inequality, the first thing is what? Temporarily equal. Okay, good. So y minus x equals 4. Perfect. Well, already said the cover-up method will work. This is going to be kind of a nice one. To find our x-intercept, we're going to cover up what? So we'll have negative x equals 4. If negative x equals 4, how much does x equal, ladies and gentlemen? We already have our x-intercept. That's great. In order to find the y-intercept, what do we cover up? So can you look at this and tell me what is my y-intercept? I have my x and my y-intercept. That means I'm going to go to 4 on the x-axis. I'm going to go to negative 4 on the y-axis. I'm going to go to 4 on the y-axis. Add those numbers reversed to my head. I'm going to go to negative 4 on the x-axis. Good catch. 4 on the y, negative 4 on the x. Draw my line. Hey, should my line be dashed or solid like it is? What tells you that? Because basically, I mean, is this new? Is this new that we do? We just finished a whole half a section on that, right? We just did this. We set equal to, we cover it up, we find intercepts, no problem. We plot those intercepts, we just did that. We draw a line, you have 2 points, no problem. You make it solid for equals, not solid for not equals, and then we check a point. Can we check a point here? So we're basically ignoring this one for now. We're just ignoring it. It's just there, whatever. We're going to check 0, 0. You're still going to write that over here. You're going to check it in your original inequality. 0 minus 0 is bigger than 4. Is 0 bigger than 4? Yes. That's a false. If that's a false, do I shade the bottom or do I shade the top? Shade the top. Can you show hands? people feel okay graphing just that one. Good, all right. Now what do you do? Yeah, let's ignore all the stuff we just did. Let's look at that one. We'll do the same exact thing. So here's number 2. Temporarily set that equal to -2. Temporarily set the equal to -2. How we find our x-intercept is we cover up everything except the x. So we cover that up. What's my x-intercept? To find a y-intercept, I cover up everything except the y, including that sign. So I get 3y equals -2. Oh no, is that okay? Do I leave it like that?
No.
What do you do? Yeah, we can do that. Is it okay to have a fraction? Let's see about that. Let's see about applying this. Let's see if I get my numbers right too. My x-intercept is -2. That's right here. Make sure you know your negatives and your positives. If you're putting -2 over here, you have the wrong idea, right? It's going to be a completely different looking line. So -2, -2 on the x-axis. -2/3, it's not up here, it's down here. Where is -2/3? Is it bigger? Is it below -1 or above -1? -1.
Above, sorry.
Just a little bit above. So about maybe right there. Do you see that point? So here's -1 and -2. We're just a little above that because we're at -2/3. So far so good? Yes, no? We got fractions. It's okay. We can deal with fractions on the number line. -2/3 is just between 0 and -1. Can I draw my line? Let's connect these two purple dots that we have. That's supposed to be straight. Right? It's not for me. It's supposed to be. I can't make any better already. Good. And then we still have to check one point. What point are we going to check here? Notice how we're completely ignoring the black shading we just did. We're just working on the purple stuff now. It's like doing two problems at once. You're just looking to see where they overlap. So we're still check 0, 0. Remember, we're checking it now in number 2. 0 plus 3 times 0 is less than or equal to -2. Or in other words, 0 is less than or equal to -2. You suppose that's true or false? 0 is less than -2. No, I'd rather have no money than owe $2, right? That's not true. This is false. 0 is not less than -2. You still with me, folks? So again, we check this point. Did this point work?
No.
So we're not going to shade, look what we're looking at, we're ignoring this black shading, just the purple line. Are we going to shade the top half or the bottom half? Definitely bottom. This side was false. This side has to be true, so we shade all of that stuff. Now again, here's what the shading represents. Please watch carefully, this is where your interpretation, okay? You gotta know what this means. See how there's no shading here? If you plug in any of these points, remember these are points, 2, 3, 4, 5, 6, -1. If you plug in any of these points, they are not going to work in either one of those inequalities. If you plug in these points where just the black shading is, they are going to work in this inequality, but not in this one. If you plug in this where just the purple is, they're going to work in the second inequality, but not the first. If you plug in these points where the shading overlaps, they're going to work in not only the first one, but also the second one. That's our solution. They're tied together with that bracket. So our solution set is right here. That section.
Do you have to write it like that?
Well, you can spell it out. I'm lazy, but yeah. Write like solution set or
But
something.
that's what you want.
I want that. I want you to identify where the solutions are. It doesn't ask for that in the book, but I want to see it.
Can you just shape this that part and show it happening?
That's fine, as long as you put solution set. Okay. but I want to see that you understand those are the solutions.
Okay, so if we just want to show that solution set, I want to shade that in, do we have to do the other ones too? Want to show that on work for one?
You can if you'd like. I mean, ultimately that's what I would like to see is you understand that, you know, this works for all these points and this works for all these points, but together they work for just those points. That's ultimately what I want to get across to you guys. So I would like to see it that way. If you want to shade just this part and you understand this concept, that's fine. Just understand that that is the solution set. Now, if you shade the wrong one, then of course I give you no credit for that, right? So that's another idea. If you just happen to shade one of them wrong, then you're going to get zero credit. You don't want that. Okay, let's try one more in our time remaining. You'll see these go pretty quick, right? Not too bad. Let's look at number one first. You need to be able to identify this. Ladies and gentlemen, number one, is the cover-up method going to work for number one? What do you think? Is the cover-up method going to work for number two? Definitely. So number one, we temporarily set it equal. To y. This is pretty much a slope-intercept form already. All I've got to do is flip them around. So I will have y equals 4x. Kind of nice. No, not even any extra work on that one. Can y'all tell me what is my y-intercept for this problem? 0. And we got that because there's no constant. There's no constant here. We know we're crossing at the origin. Not if you're okay with that. Okay. What's my slope? So up or down? Up how many? Over to the 1. We got that. So 4 over 1, the intercept was 0. Go up 4, go to the right 1 because it's a fraction 4 over 1. So we graph our line. Do I leave it solid? Do I make it dashed? Everybody? Good. And can I check a point? Can I check 0, 0? What do I check? 0, 1. Okay. Check 0, 1 in this. 4 times, x is 0 here. 4 times 0 less than or equal to y equals 1. 0 is less than or equal to 1. Is that true or is that false?
True.
0 is less than 1. That's true. Here's what you did. Watch your board here. You checked this point right there. You checked 0, 1. 0 for x, 1 for y, and that said that that point was true. That point's true. Do I shade, let's call this the left. Do I shade the left half plane or do I shade the right half plane? The left half plane. Because that was true, right? That point's on that left half plane. I'm going to shade all this stuff. Okay, we got one more. Number 2, same idea, same exact stuff. We're going to temporarily set equal to 9. Cover method's going to work. So for my x-intercept, I cover that up, I get x equals 9. For my y-intercept, I cover that up, I get 3y equals 9. Or if I divide by 3, I get y equals 3. That's kind of nice. Except the 9 is way out there. X equals 9, that's way over here. Y equals 3, that's up here. 1, 2, 3. And then I graph the line. Kind of a line. Hey, I wasn't able to check 0, 0 here. I checked 0, 1. Can I check 0, 0 here? So you can use 2 different points. You don't have to use the same point. Remember, I'm ignoring all the black graphing right now. I'm just looking at the purple graphing. So I can check 0, 0 there. If I check 0, 0, it's an original inequality. 0 plus 3 times 0 is greater than or equal to 9. 0 is bigger than 9. Is that true or is that false? False. Definitely false. So we checked 0, 0 this time. 0, 0 was false. Am I going to shade the bottom or the top half plane? This was false. Do I shade the bottom or the top? Definitely the top. Can you see my solutions? All these points will work in both current and inequalities. How many of you feel okay with what we talked about today? Do you guys feel okay with these examples? Good. So we're going to work on graphing some linear inequalities. And what we realize is basically, this is just 2 inequalities to 1. If we can graph the first one and we can graph the second one, that's really all I'm asking you to do. I'm just asking you now to put them on the same XY axis. And that's pretty much it. So let's look at our first inequality. I need you to be able to realize a couple things about this. Firstly, with our first inequality, let's call this one number 1. Am I going to be able to graph that with the cover-up method in standard form like we've been normally doing? No. Why? Well, it's not standard form first, but even if it was in standard form, what number would be off here to the right? You would normally have a constant like this one, but up here, do you have a constant? No. So that means the cover method is not going to work. So when we do this, we call Call this one number 1, or we call this one number 2. If we work on number 1 first, sure, we're going to temporarily set it equal to y. We temporarily make that equal sign. Do we ever do this any place else besides this one little part? Ever?
No.
Never. Just here. We temporarily set it equal. This is just so that we can graph it, basically. And if we cannot do the cover-up method here, and even if you subtracted y, you'd have 2x minus y equals 0. Remember, we talked about this last time. If you covered up the 2x, you get y equals 0. Cover up the y, you get x equals 0. That just gives you 1 point, right? You can't have a line with 1 point. That's not good. So the other option was, whenever you cannot use the cover-up method, we're going to put this in slope-intercept form, which is y equals mx plus b. In our case, it's kind of nice. We have 2x equals y. Let's just flip-flop that equation. Y equals 2x. We already have that thing in standard form. That's great. I'm sorry, in slope-intercept form. Okay, ladies and gentlemen, let's graph this line. Can y'all tell me what is my slope for that function? Great. Someone else tell me what is the y-intercept for that function? Good. 0. 0 says I'm crossing at 0. Hey, that should make sense because that's the whole reason why we're doing this process, right? Because we know it crosses 0. Actually, instead it crosses 0 twice. We have x equals 0 and y equals 0. That's what we would have got with the cover-up method. Review that from last time. We have already talked about that. So that says, okay, we're crossing our y-axis at 0 at the origin. Next up, we're going to use our slope to find the next point. Again, what is my slope? 2 over what?
1.
Okay, are we going to go up 2 or down 2 then?
Up 2.
And over to the...
Right 1.
That's right there. We'll graph our line. Do I leave it solid like it is, or do I need to make a dash? What do you think? What tells you that? Okay, so we're not looking really right here, right? That was just our temporary equals. We're looking back up here at my inequality. That says it's not equal, doesn't have that little equals part. So I need to make that a dashed line. Am I done with that? What else needs to be done on this problem, folks? We need to check something. Why do we need to check something? What else do we need to do to make this graph look appropriate? Okay, so we need to check a point. What point do we typically check? Can we check 0, 0? No, it's on the line. It's saying it tells anything. So what point do we check if we can't check 0, 0? Yeah, 0, 1 will work. Yeah, that's have yourself an alternate plan there. If 0, 0 doesn't work, pick another point every time that you can check. I like to pick 0, 1 because I know it's going to work every time. If 0, 0 doesn't. So we'll check 0, 1. That means 0 for x, 1 for y, and we check that back in our original inequality. So that's 2 times 0 less than 1. 2 times 0 less than 1, we've got 0 is less than 1. 0 is less than 1. Is that true or is that false? Make sure you're identifying the point that you're checking. Make sure you know what that is. That's important, right? That doesn't tell you what side to shade. So we just identified that we're checking 0, 1. That's right here, 0, 1. This point was true or false? So are we going to shade, let's call this the top half. Are we going to shade the top half or are we going to shade the bottom half plane? Which one? Definitely. The point was true. That means all these points are true. We shade this part. Which makes you feel okay with that part? Good deal. So that was half our problem basically right there. We did our first equation, our first inequality, and now we're going to do the second one. We do exactly the same thing we just did. It's just we have to do it on the same axis. So it's going to get some crossover, and where actually the shading crosses over, that's our solution set. That's what we're looking for. So let's work on the second one together, and then we'll do one more after that. I'll let you go on your own. So let's look at inequality number 2. Again, we temporarily set these things equal. 2, 3, 4, 5. That's way up here. And we're going to. The reason why it's easiest is it makes one entire side of our inequality equal 0. We like that. So we're back here at our original inequality. That's 5 times 0 plus 0 is greater than 5. Or in other words, 0 is bigger than 5. Is that a true statement or a false statement? Definitely. Definitely false. So we checked 0, 0 in this case. We checked that point. This is going to be weird because it's on the other line, right? But you have to ignore that other line. You have to ignore the purple line right now. We're just looking at the black line with our black point over here. So we checked that point. This point did not work. That means that every point on this half plane of our graph here doesn't work for my black line. That means the other side is the side we're going to shade. So we check this point. It did not work for our black line. We're going to shade the other side. That's all this stuff. Be generous with your shading. Make sure you shade a lot. Don't just shade a little teeny part of your line, right? Shade the whole half side. That's what we're doing here. How many were able to follow that along and get that shading as well? Do you see the solution set? Yeah, it's not here. This is nothing. This is just purple. That's just black. The black and the purple, that's our solutions. Let's try one more together. I'll show you a couple more things on this, and I'll let you do a couple on your own. So we got negative 2x plus 5y is less than 10. We got y is less than or equal to 3. Let's see how this thing plays out. So if I look at my first inequality first, my second inequality second, the first inequality is telling me I got negative 2x plus 5 less than 10. I'm going to temporarily set that thing equal because that's how we do our graphing. We make sure it's equal so we can find our intercepts. It's just a temporary step. We don't do this for every time we see an inequality, just if we're trying to graph our linear inequalities on a graph like this. Hey, will the cover-up method work? Yeah, absolutely. So to find our x-intercept, which one do I cover up again? So I'm going to cover that up. I'm going to write what's remaining. I'll be dividing by negative 2. There's at most one more step after that. We get x equals negative 5. This is my x-intercept. To find the y-intercept, we do the opposite. We cover up the x term, everything but the y. Still, we'll divide and we have our intercepts already. So let's go ahead and plot those things on the graph. I know that x equals -5 means I'm going to go over here, -5 on the x-axis, put a nice point. And y equals 2 says I'm going up 2 on the y-axis, I'll put a point, and then we can graph our line. By the way, is it a solid or a dotted line in this case? Solid, everyone needs to know that. Okay, good. Can you see why it's dotted? Yeah, we're looking up here, right? Not right here. What point am I going to check? Let's do it. So we check 0, 0. If we do that, we're going to have -2 times 0 plus 5 times 0 is less than 10. We're rewriting the original inequality. It says 0 is less than 10. Is 0 less than 10? Is that a true statement or a false statement, folks? Perfect. So we identify the point that we just checked. We checked 0, 0. 0, 0 was true, signifying that this entire half plane of that line is true. So we're going to go ahead and shade the whole thing. Hey, we're done with one. They go pretty quick once you get the hang of it, don't they? Cover up, grab it, shake it. That's awesome. Kind of nice. Now, the second one, inequality number 2, we have y is less than or equal to 3. Again, we're going to set the thing equal just temporarily. Just temporarily. Do you remember, so I put this on the board here for us, do you remember what y equals 3 is? Or horizontal what? So we have a line there, horizontal line. Remember we talked about that yesterday? Got a horizontal line at y equals, and you know what, the reason why we can say this is horizontal, if you think about it, there's only a y. There's no x's. So that means if y equals a number, sure, you're going to be crossing the y-axis, y value, at 3. But if it doesn't have an x, that means you're not crossing the x. So if there's no x, can you possibly be like this, or like this, or like this? No, that would be crossing the x. That would say you would have an x-intercept. So if you have no x, there's no x-intercept, it means you have to be a horizontal line. Otherwise, you're going to be crossing that axis. We're going to keep that one solid because of this right here. That says equal, so that's a solid line right at y equals 3. Hey, do we still have to shade it? But you know what? It's kind of nice. If you look back up here, this right here tells you the direction of shade just like a number line would. The only thing is with the y, you kind of have to tilt your paper like this for me. If this is a number line of 0, 1, 2, 3, 4, 5, 6, and -1, -2, -3, all that stuff, this is shading to the left of 3. Left of 3 would be below 3 in this case. Do you guys see that? See what I'm talking about? Otherwise, you can check a point too. You could do that. So if you check 0, 0, if you want to check that here, your x-coordinate is 0. What do you do with the x-coordinate? Nothing. There's no x to plug it into. You with me on that? The y-coordinate is 0 also. That's okay. This just says 0 less than or equal to 3. Is 0 less than or equal to 3? That's true. We checked 0, 0 again. It was true. That means I'll shade below the purple line. That's what that says. So either way you want to do that, that's fine. You can check the point, or you can look at it like a number line. Either way's gonna work. Just make sure when you're shading this, we're ignoring the black line right now. We're just looking at the purple. We're shading all of this stuff. Do you guys see what the crossover is on this graph? If nothing's up here, it's not right here. That's just the purple stuff. It's not right here. That's just the black stuff. It's this obtuse looking angle with all the shaded below it. That's a large half plane. You'll feel okay with these 2 examples. Good. All right. I'm going to give you one to do on your own right there, and then I'll erase that one and give you another one. Why don't you try these on your own? I'll be walking around. If you need help, let me know. So get started on that one. So we're graphing each inequality individually, just making sure we're shading both of them. Where the shade overlaps, that's what we're calling our solution set. Although I did make a deal with my next class because they always come in late. I said, 5 minutes late, you bring me coffee. 10 minutes, coffee and a donut. 2 minutes, a new car. Obviously, car. See, I would have been smart and said, like, oh, here's a new car and bring like a Hot Wheel. Let's take a few more minutes, try to wrap this up. Hopefully finish the first one and work on the second one. We're going to start on the first one in just a bit. Okay, we're going to start on the first one up here. So first one, we're looking at first inequality, then second inequality. We do them independently, just look for the crossover. So first inequality says we're going to temporarily set that thing equal instead of the inequality that we have. So we'll have x minus y equals 4 just for a moment, just so we can find our graph. We cover up everything but the x to find the x-intercept. In this case, we're done. That's great. Cover up everything but the y, including sign, to find the y-intercept. So if negative y equals 4, we know that y equals negative 4. Now we've got our x and our y-intercepts. X-intercept says we're going over to positive x. And 4. Y equals negative 4 says we're going down on the y-axis to negative 4. Put a point there. We'll graph our line. Of course, we're going to make it dotted because there's not an equals part up here. So we've got our dash line. We're good to go. And we're going to shape this. In this case, we can check the point 0, 0. That's great. 0, 0 says we're going to have 0 minus 0 is greater than 4. That 0 is greater than 4. Clearly, 0 is not bigger than 4, so we're going to put a false. We checked 0, 0. It was not true. It was false. So this half plane is not acceptable. The bottom half plane, that's what we're going to be shaping. And you know how many people made at least that far? Good for you. That's fantastic. Okay, next up, number 2. Number 2, we have the same exact idea. We're just doing this process twice. So we're going to temporarily set it equal. So x plus 3y equals negative 4. Cover everything but the x to find the x-intercept. So we're going to have x equals negative 4. No problem. Cover everything but the y to find the y-intercept. We've got 3y equals -4. In this case, though, 3y equals -4, we still have to divide. So we're going to divide everything by 3. We get x equals -4, no problem. Y equals -4 thirds. Is it okay to have that fraction? As long as you know how to graph a fraction on a number line, that's fine. So x equals -4 says we're going over here to -4. -4 thirds is -1 1/3. So we're going to go -1 on the y-axis, and then a little bit more. Third of the way between -1 and -2. So that's right about there. You don't have to be exact, but don't just put on -1, don't just put on -2, be between there at some point, okay? And we're going to graph that line. Now we're also going to make that one dash, because again, we don't have that equals. And we can still check the point 0, 0. So 0, 0, we have 0 plus 3 times 0 is less than -4, or 0 is less than -4. Is 0 less than -4? Is it true or false?
False.
Yeah, definitely false. So again, we checked 0, 0. It was false, signifying this half plane is wrong, this half plane is right. See all that stuff? And then right here, that's our solution set when we cross over. But you raised your hand, you made that far, you got that. Good for you. You're going to have a problem very much like one of these that I'm giving you on the test. Yeah, let's do our last one. We're just going to probably talk about that one. Unless we have a little extra time, then I'll do it for you. Make sure you see at least one example like that. So let's look at inequality number 1 and inequality number 2. For inequality number 1, you're going to see that when you set this thing equal temporarily, we're going to have y equals 6. Well, that's a constant. And we should know right now that graphing a constant, that's going to be a horizontal line at y equals 6. So when we come down here to our graph, this says you're crossing, your y-intercept is at 6. There's no x term. If there's no x term, you don't have an x-intercept. That means the only thing you can draw is a horizontal line. So we'll do that. We're going to keep it solid in this case. The reason why we're keeping it solid is because, well, we have that equals right there. So it says it's not dashed like the previous ones. We keep that solid. And we're still going to check the point. Or you can look at this like a number line. In either case, if you check the point 0, 0, you're going to get 0 is less than 6. That's a true statement. So we should be shading the bottom half of that half plane. If you look at like a number line, it's saying you're shading to the bottom of or to the left of 6. That also says you're shading this part of your graph. Either way, you're shading this. I like those constant ones. Don't you like those constant ones? Kind of nice. Not a whole lot of work. As long as you remember they're horizontal line, right? As long as you remember that. Okay, number 2, real similar to some of the other ones we've done before. We do have the covariant method that'll work here because we have that constant off to the side. So we do the temporarily equal. Temporarily equal to 10. Covariant method again is going to work because we don't have a 0 here. Remember, if you do have a 0, or you don't have that constant term, you have to use the slope-intercept form. We've done a few of those examples. Just remember that later on when you get your homework. So cover up says I'm going to cover up everything but the x to find x. So -2x equals 10. If we divide by -2, x is -5. If we cover up the x, we get -5y equals 10. Divide by -5. Hey, we get y equals -2. So already we have our x and y-intercepts. Imagine if you're still following me on this stuff. I'm going kind of quickly through this because we've done this several times right now. I just wanted to give you some practice on that. So y is -2. That's down here, -2. X is -5. That's over here to the left of the x or the y-axis, -5. We're going to graph our line. In this case, we have to make that dashed. You see why we have to make a dash? Okay. But we can also check 0, 0. That's nice. So checking 0, 0, we're going to get -2 times 0 minus 5 times 0 is greater than 10, or 0 is greater than 10. True or false? Definitely false. So here's 0, 0. Why don't you tell me now if that's false? Am I going to shade the top half plane or the bottom half plane? So I'm shading all of this stuff. Wait a minute, that's weird. Do you see any crossover? This is why you have to be kind of generous with your shading. I made this mistake on this graph. My lines aren't long enough, and my shading is not big enough. See what I'm talking about? I need at least some intersection so you can see where the shading is and where the shading isn't. These lines actually continue on to the left and to both of them to the left here, where they cross. And the shading is all of this stuff down here. So we would have a crossover if you continue this. This line would continue, this line would continue up, and our shading would be everything below that part. So if you have your paper right now, continue those lines until they actually intersect. Raise your hand if you're able to get that. Get this diagram. We're able to follow that down, see that it's correct and everything? Okay, good. The cover-up method, -5 for x, -2 for y. Definitely going like that. Shading below it. Shading below the y equals 6. It's just you gotta draw be generous with your shading. Make sure you see, and generous with the lines. Make sure you see where the crossover is. Okay, the last one I'm going to give you up here. I just wanted you to see this because I want you to know there's options on how to graph things. Okay, when you look at this problem, do you see that it's already in slope-intercept form for you? It's already in there. If you are going to do this problem and temporarily set each of these equal, we have y equals -x plus 2. And we would have y equals 2x plus 5. Hey, folks, will the cover-up method these two? Does it have a constant? Will the cover-up method work for these two? Not the way it is, but yes, it will eventually. Okay, so if you said no, yeah, you're right. Right now it won't. Okay, right now it won't. But eventually it would. So if you wanted the cover-up method to work, if you liked that method, here's what you could do. If you like the cover-up method, what could you do to this problem? Just add x and you're going to get x plus y equals 2. Use your cover-up method, you get your intercepts, okay? So you could do that. Add x, you get x plus y equals 2. Hey, look at that. Look at that. Cover up the y, x is 2. Cover the x, y is 2. You have your intercepts, you can graph that. With me, folks? If you don't like that, if you like this, check it out. Could you still get the same line graphing that? What's your y-intercept? What's your slope? That's down 1 over 1, right? You graph it 2 ways here. I'm giving you options. I don't care how you graph it, as long as you're able to graph it. This will give you the same line. I'll prove it to you right now. If you did cover up, x is 2, y is 2. Here's 1, 2, 1, 2. That would be this line going through those 2 points, right? However, if you graph it using slope-intercept, ignore this part for a second. Slope-intercept says that this intercept is 2, right there. You go down 1, over 1. Down 1, over 1. You see you get the same ones? Same exact line there. So either way you want to graph that, I don't care. I'm going to give you one like this on your test. That way you have some options here. If you like slope-intercept, great. Use slope-intercept, that's fine. If you like the cover-up method, you're going to have to do a little bit of work with it. Just add the x over, but then you use the cover-up method. So far, so good? Okay. Same thing would happen here. If you wanted the cover-up method, what would you have to do? Yeah, you would do that. -2x plus y equals 5. Here it would say that your x-intercept is -5 halves. -5 halves is -2.5. That's okay. Y-intercept is 5, you can graph that on your line. Or you can come back up here and use slope intercept. What is your intercept here, ladies and gentlemen? Your intercept is not 2. Intercept is 5, that's right. Intercept is 5. Your slope is how much? That means up or down? Up 2 over 1. You would get that line either way. Notice how this is going to cross at 2.5. You guys see what I'm talking about? If you wanted your y-intercept or your x-intercept, it would be 5 divided by -2. That's negative 1, 2.5. If you want your y-intercept, that's 5. That's where we're crossing anyway. They will work either way. Now, of course, you're going to clean this up and make, well, these would be solid lines. But you're going to check your 0, 0 in each case. You're going to find your shading, and you would have shaded this graph. In this case, let's see. Well, which one was number 1? Oh, I forgot to use different colored markers. This is number 1?
Yeah.
0 is bigger than 2, that's false. So we have this way. 0 is less than 5, that's true. We have this way. So I'm pretty sure, is this one shaded? Is this right? Yeah? Are you disagreeing with me because I'm a teacher?
Yeah.
I'm pretty sure it's that one. That would be your shaded portion there. Double check that for me. Let me know if I'm right, because I just did that really quick in my head. It is right? I love when I'm right. Don't you love when you're right? Right. Would you raise your hand and feel okay graphing linear inequalities? Sweet deal. That's the last thing that's going to be on your test. So if you can do this, combined with the chapter 8 stuff, you're going to be good on Monday's test. Now today, for the rest of our day, we're going to start chapter 10. Chapter 10 will not be on your test on Monday. What we're going to do in chapter 10 is do the first section, which is an introduction to some square roots and some radicals, some radical ideas. And that'll be on we'll start on this next week after your test. Any questions before you going on that stuff?
I did have one.
Yeah.
Just like whenever you have the number at the end being like less than or equal to 0,
Yeah.
it makes both of them 0, 0. So I'm just how do you?
Right, exactly. If you reviewed last time, when we were here last time, we said if that's ever equal to 0 on the right-hand side, such as this, if that were to be 0, you get x is 0, y equals 0, that gives you only 1 point. You cannot graph a line with 1 point, therefore you must use slope intercept. You have to use it. Okay, let's start 10.1. We're done with graphing for a while. Are you ready to be done with graphing for a while? Oh, I like graphing. That's all right. We'll get back to it in chapter 11. Okay, we're going to talk about radicals. And some pretty radical functions. Told you math was fun. It even has a word like radical in it. How can you not have fun when you're saying radical all the time? Yeah, okay. I know I'm a dork. So we're talking about radical functions. What a radical is simply a root, like a square root or a cube root. That's what we mean by radical. It's this funny looking thing that looks like that. That's a radical. Typically, what we have is square roots. I believe we've already talked about square roots in this class, but it's going to be nice to go over these again because I'm going to draw some examples from our square roots, okay? So review square roots. What does a square root do? Say that again?
The number times itself.
Okay, a base number, sure. Basically, what this is doing is undoing the act of squaring a number. So what you're saying is that some number squared would be 25, what's that number? Or undo this for the square, and the number is 5, that's right. So we're saying 5 times itself would give you the 25 inside of our square root. That, by the way, if you want to know the name of that, that's called the radicand. Can you say radicand? Radicand. It's like that. It's not radicant, all right? You can, right? Radicand. Yeah, not radicant. So we're finding what number times itself gives you the radicand. In this case, yeah, it's for sure 5. How about the square root of 0? Is the square root of 0 possible?
Yeah, 0.
Sure, why not? Is 0 times 0 0? Yeah, that works. So yeah, that's possible. So when you get square root of 0, for sure, you can have that. That's fine. How about the square root of fractions? Were we okay doing the square root of fractions? Square root of 9 over 49 would be good. We take the square root of the top one, take the square root of the bottom one, the numerator and denominator. We have 3 over 7 for sure. Negative square root 49 and the square root of negative 49, are they the same or are they different?
No, one's possible.
Only one is possible in what we know as the real number system. The other one will be possible when we deal with the complex number system. That's going to be in end of chapter 10, 10.7. So that's in this chapter. We are going to know how to deal with this one by the end of this chapter. Right now, we can only deal with this one. What's the difference between these?
Negative 7, the other one's not possible.
Why is one negative 7? Okay, very good. So in this case, when the negative is outside of our square root, it's not being applied inside there. This is saying take the opposite of the square root of 49. It's basically what it is. So you go, what's square root of 49? And then make that the opposite. So negative 7. The square root of negative 49, right now, there's no number times itself in the real number system that's going to give you negative 49. You do 7 times 7, you get 49. You do negative 7 times negative 7, you get 49. That's not going to happen for us. So here we have, well, I need you to write, don't just put NA, don't just put no solution. I need you to be very specific right now. We're going to put no real solution. No real solution. And what that says, a real number is the numbers you've been dealing with since you were like in kindergarten. Every number you can probably think of right now in your head. Every integer, every rational, every non-ending and non-terminating or non-terminating, non-repeating decimal, everything you can think of is a real number. We're going to deal with another set of numbers at the end of our chapter though. Okay, one more thing that we can do, square roots of decimals. A square root of 0.36. Is it still possible to take the square root of a decimal? Yeah. For sure, yeah. It is actually 0.6, for sure. 0.6 times 0.6 is 0.36. That works. Can you take the square root if it involves variables? How? I need you to understand, yeah, you're right. I need you to understand what we're actually doing here with the square root of 25. So if we're doing the square root of 25, what really is happening is that this is possible because this is 5, that's 5 squared, right? And ultimately what's happening is our square root is undoing the squared part of this. You can think of it like that. They're inverse operations. So whenever you have a square and a square root, you say, oh, okay. I know that these two things, if you want to say cancel out or simplify away or whatever you want to call that, that's what's happening. The square root is undoing that square, and we get whatever we're left with inside of our radicand. That's our answer there. That's why that works. Are you with me on that? You can do that with every one of these examples. This is 3 squared, therefore the square root is going to do that square, we're going to get 3. This is 7 squared, the square root is going to do that square, we're going to get 7. Imagine if you're okay with that. Right. Can we write this in a similar way that we were able to write that? And the answer is yeah. Yeah, if we write this as a square root of, instead of x to the 10th, I need to be able to use those rules for exponents. X to the 10th, you could write this as x to the 5. Well, wait a minute, we want 5 times 2. How do we write exponents as multiplied? Do you remember when an exponent is raised to an exponent? What do you do with that? Like x to the 2nd to the 3rd. Do you add those or do you multiply those? You definitely multiply those. These ones you would add, right? Those you would add. These ones you multiply. What I'm going to do is try to write this in some way that I have a square out here. Is this still x to the 10th? Sure, but now watch. I have a square root and I have a square. What happens to a square root and a square? Cancel each other out. So they're going to eliminate each other in their inverses. So on the right hand side, what do I get out of that? So by writing this as something squared, we can eliminate that. I'm going to show you one other way to do this. You're going to think right now that why are we going to do this way? This seems a little bit longer, but trust me on this, get used to this way as well, because we will be using it later on. I'll show you this in a second. Well, actually, I'll show you this in like a week and a half, but it'll be good to practice it. There's another way that we can do this. Do you remember that I also told you we can, when we multiply things like this, we add those exponents? Well, watch up here on the board. We can do this two ways. We can do it this way, great. Or you could write this as, instead of x to the 10th, would it be okay with you if I wrote x squared times x squared 5 times?
Yes.
Is that still x to the 10th to you?
Yeah.
X squared, we add up all those exponents, right? 2, 4, 6, 8. That's x to the 10th. Nod your head if you're agreeing. Do you see that everywhere we have an x squared, why am I thinking x squared? What's my root out here? It's a square root. Square roots will undo your squares, right? Everywhere we have an x squared, it will simplify out. So what I'm going to do here, we'll cancel. We go, oh, that's gone. That's gone. That's gone. That's gone. That's gone. How many x's do I have left? 5. And they're being multiplied together. I'm going to have x to the 5th. Same answer. The same answer. Now, you might be wondering why in the world are we doing that? By the way, this works. I need to show you why this works. By the way, just a little note. This works because you can always separate as x squared times square root of x squared times square root of x squared. You can do that as much as you want. You can separate that product into different x squareds. Okay, so each one you can simplify that out. X, x, x. You see the idea? You do that every single time. Now, why are we doing this? Why? I'll leave that. That's a good little note. Why might we want to do that? This one seems so much quicker. That's true, it does. But the question is, could you simplify this with that method? Can you simplify this with this method? Can you write this as, what we did here is we wrote this as x to the some number times 2, right? And that worked because this was equal to 10. Can you write this as square root of x to some number to the second? What times 2 equals 11? 5.5. Well, that doesn't really work so well, okay? We can't do that. That's not going to help us out at all with this problem. So I had to teach you another way to do this. You see, using that method, I can simplify this. I'm going to go a little bit ahead of where I'm supposed to because it's going to make sense later on. I could write this as, that's not going to work. I could write this as x squared, okay, x squared, x squared, x squared, x squared, and what else? Perfect. Okay, perfect. We're going to look at what simplifies out of this. This, again, do you see why this simplifies, by the way, each of these? I could write this as a square root of x squared times square root of x squared over and over again. In each case, those squares are going to simplify, but this one does not. This one does not. I want you to look at what happens. Whenever we simplify something, that's going to go outside of our radical. So we get x times x times x times x times x outside of a radical, but this one is still inside. We have the square root of x. That would be x to the 5th square root of x. Yes, no? I think a little whippy on that one. A little bit, not so much on that. We're going to come back to that. I just want to kind of preview that. This is about 2 or 3 sections from now. I just want to let you know that the reason why we're doing 2 different methods here is because we will eventually be dealing with stuff like that. And I think you're okay with at least this part of it. All right, we'll start this tomorrow, and we'll finish that on. So we're noticing that in just like this situation, we could write this as something to the second power, the square, and the square root. They're inverse operations. They will simplify out of that expression. And we're going to get just the radicand. Remember, that was inside of our radical left. Or we can separate this as x squared times x squared The reason we're simplifying to x squared, or write this as a bunch of x squares, is because a square root will simplify a square. Square root, square, those things are crossing out. So every time we solve a square root with a square, we cross that out, they're inverse operations, and we get just the radicand left over. We can do the same situation here. Even though we don't just have a variable, we have a number and a variable, we can do the same idea. What is the square root of 36? So we could write that as 6. Also, so I'm going to leave that for now, just 36, because I know I'm going to be able to take that square root in just a bit. Also, I need to deal with this x to the 6th power. Now, there's two ways to do x to the 6th power. We could do it like this, as something to the 2nd power. How would I do that? Okay, so we're trying to write this as something to the 2nd power. We're noticing that exponent raised to an exponent is multiplication. So how do we write x to the 6th as something, x to something squared? And we, of course, yeah, we're going to do the 3rd. It was already said. Is that still x to the 6th? And now we can do the square root. Can you tell me what's the square root of 36? What happens to this square root and that square? What's going to happen there? Can you tell me what I'm going to have left over? But some of you are not with it today. You guys got to be with it. It's Friday morning. Let's go. Come on. So what's going to happen to my square root and my square? What happens there? Okay. So there are inverses. They're going to be gone. What do I have left over? That's the answer. Now, if I did it the other way, some of you are going to prefer this method, by the way. That's fine. I like that method. It works all the time. This one only works if you have an even power. If you have an odd power, does that work? You can't write it as something to the 2nd because something times 2 doesn't give you an odd. That's the problem. That's why we have to learn this method as well. So if we did it the other way, we could write this as 36. And instead of x to the 6th, what I do is write this as x squared, x squared, x squared. And you'll see that I can still take the square root there. Square root of 36 is still 6. Square root of x squared, square root of x squared, square root of x squared. Notice how this square root, because I can separate it like that, every one of those 2's is going to be crossed out. The square root is going to undo every one of those squares. And again, how many x's do I have left over? So I have x in the first. Either way we do that, we're fine. How many feel okay with that so far? Good deal. Good deal. Try a couple of these on your own, all right? So they don't take too long. Let's work on those. So first two, just some numbers, take some square roots of those, and last one, we have a variable in there. Use one of those two methods. You don't have to show me both, just use one of them. I don't care which one. This one. Ultimately, we're going to be doing this or this when we see these problems, most likely, from here on out. So first one, square root of negative 81, how much is that? No solution. No, not no solution. No. Yeah, we will have a solution on this in section 10.7 for sure. But right now, we are dealing with real numbers, so we have no real solution. Why no real solution? What's the matter there? Yeah, we know that a number times itself cannot give us a negative. So if the radicand is negative inside of a square root, how much is that, folks? Yeah, that's exactly right. And 16x to the 8, we're going to do this process over here, one of these processes. So we know the square root of 16 is how much? Okay, that's not bad. The square root of x to the 8, you have to write this a certain way. Either you're gonna write this as 16, x to the something raised to the second power. We're choosing the second power because we know a square root and a square are inverse operations. That allows us to simplify that. Not sure if you're with me on that. So we're choosing the second power because it's a square root. What has to go in here to make that true? So we do square root of 16 is 4. Square root of x to the fourth to the second, that's going to simplify out of our expression. We're going to get x to the fourth left over. Raise your hand if you got that. Good. If you want to do it the other way, that's fine. If you want to do it the other way, that's fine. What we're going to do is still write this as 16, except instead of x to the 8th, we have to write this as a whole bunch of square terms. So x squared, x squared, x squared, x squared. That still makes x to the 8th. And everywhere we see that square, underneath that square root, that's going to simplify out of our expression again because we could separate this as square root of x squared, square root of x squared, over and over again. So still we get square root of 16 is 4. We have x, that's x to the 4th. Either way we do that, we get the same answer. Hey, by the way, let's do a little practice on this. What's the square root of 81? How about the square root of 64? 25. 49. 30. Does it exist?
Yeah, it's 5.
Okay, so it's not just that there's only like 10 square roots for the first 100 numbers, right? I mean, is it just that you take square root of 1 and 4 and 9 and 16 and 25 and nothing else? No. It's just that when you take the square root of those numbers, you're able to give me a whole number, which is why you're able to do it quickly, right? You go with the square root of 25, you go 5. The square root of 49, 7. The square root of 30. I have no idea. I don't know. Why? Because it's not, what is that number known as? Where it's 1, 4, 9, 16, 25, 36, 49, 64. What are those numbers? What are those? Well, why? Why do those ones work? Think about it. Why do those numbers work? Okay, what's that known as in mathematics when you multiply a number by itself and it gives you something? Say it again. No, not a prime number. The prime number would be a number where only 1 and the number itself divides it. So number's 1. Can you take the square root of 1? Sure, it's 1. Yeah. What's the next number you can take the square root of and it's a whole number? Yeah, not 2, right? Square root of 2 is, how about 3? I don't know. How about 4? 2. Great, okay. What's the next number you can take the square root of easily? 5? No. 6? No. 7? 8? 9? Yeah. What's the next one after that? Sure. What's the next one after that? Yeah, then 36, then 49, then 64. How are we getting these numbers? How are you determining that? Are you just guessing and checking, or is there an easier way? By the way, what's the square root of 1? Square root of 4. Square root of 9. 4, 5. Okay, what are those numbers? How are you getting those numbers from 1, 2, 3, 4, and 5? How are you getting those numbers? Okay, in other words, instead of just multiplying them together, how else could I say that? Squaring it. These numbers are called perfect squares. Have you never heard of that before? A perfect square is a number that is an integer times itself. Perfect squares. So a perfect square, that's that number where you take a number times itself, you get one of those, right? You get 1, 4, 9, 16, 25, 36, and so on, so on, so on, forever. Those are also the numbers where I can take the square roots of easily, and it gives me a whole number answer. And the reason why is because we know that a perfect square is a number times itself, right? So if I'm undoing that, it's going to give me that number back again. And a square root and a square are inverse operations. So these are the only numbers that you can take a square root of, and it gives you a whole number answer. If you don't have a perfect square, such as when I said, what's the square root of 30, and y'all went, I don't know, somewhere between 5 and 6 probably. Can between 25 and 36, right? So it's somewhere between 5 and 6. But I don't know exactly how much it is. And that's because it's an irrational number. So every time you take the square root of a number that is not a perfect square, you're going to get an irrational number. That's a number that is represented by a decimal that's not ending and not repeating. If you take the square root of a number that is not a perfect square, the result will be irrational. Let's look at the square root of 30. Firstly, I said that this number is between 5 and 6. Now, how did I know that? Well, let's look at that. Do you know the square root of 25? Do you know the square root of 36? If this is between 25 and 36, then we know that the square root of that number has to be between 5 and 6. Does that make sense to you? So it's kind of squeezing that. It's squeezing it between two bookends. It's saying, well, this one equals 5, this one equals 6. If there's something between there, the answer has to be between 5 and 6. That's the way that works. So I know this is somewhere between 5 and 6, but I don't know exactly how much it is. There's methods to do this, like by hand, to find out exactly how much a square root of 30 is to whatever decimal place you want. But it's very hard to do. And we have these nice little things called calculators, which do it for us. Take out your calculator if you have one. Square roots can be found on your calculators. Now, I gotta warn you that when you find a number on your calculator that's a square root, it's giving you like the first 10 or 12 digits. That's not everything. This number will go on literally forever. It does not end. It doesn't repeat. You cannot represent it as a fraction. That's what irrational means. Rational means fraction. Irrational means cannot be represented as a fraction. So this thing doesn't end. It goes on to millions and millions and millions of digits long. Okay, it's not a huge number. It's only between 5 and 6, but the decimals go on forever. So here's how you find your calculator. The first thing I need you to do, find the square root button. It looks like that. It might be a second or a shift button. So find that on your calculator if you have a calculator. If you don't have a calculator, look at someone who has a calculator right now. You need to be seeing a calculator. Okay. So if you don't have one, share. Find your square root. And what I want you to do is press your square root button. Press your square root button right now. When you press your square root button, if it came up and you have now a square root on your screen, that's great. If you are one of those people, raise your hand. If you press the square root button, you have a square root on the screen. Okay, you people are going to press a square root first, then your number, and then press equals. Okay, that's what you people are going to do. So you press your square root will pop up, then you press your number, press 30 right now, and then press equals. You should get 5 point something. Do you guys have that? If that was you, okay. The other people, if you press your square root and then it still popped up 0, how many people? You're one of two cases. Okay, so if you press that and it popped up 0, what you have to do is press your number first and then press your square root. So press 0 and then press, it's probably a second button or shift button, and then your square root, and you should get the 5 point something on that. In either case, did you guys get that? Okay, how many people have a calculator? Raise your hand. And how many of those people were able to find the number? Okay, good, that's everybody. That's fantastic. So can you tell me to the third decimal place, what is square root of 30? 7 what? Okay, so we do need to round appropriately. So if I say third decimal place, I mean 5.77. If that number is a 2, then we leave that number alone. If this was 5 or more, then we would have to move that to an 8, yeah? Okay, so round that appropriately. Let's try one more for me. Let's do the square root of 45. Before you do this on your calculator, I want you, unless you've already done it, I want you to think of what number this is between. what number that is between. Why 6 and 7? Perfect. Yeah. This is between those two values, 36 and 49. Square root of 36 is 6, 49 is 7. Therefore, it has to be there. Very good. How much is that? Not exactly, because we are approximating. By the way, that's what that squiggly equals means. It means it's not exact because we're rounding, we're approximating here. How much is that? 6 point what? 709. All right. I believe it. 6 point. Hey, I just write what you guys say, all right? That's what my job is. That's it. How many will feel okay finding this on the calculator? Good, good deal. You know, we've covered square roots. You feel okay about square roots. At this point, you should be able to find the square root of any number I give you. If it's a perfect square, it's pretty easy. It's just like 4. If it's not a perfect square, right now all we have is a calculator method. Now I'm going to teach you a method in a little while, a couple sections from here, where we can simplify these numbers to get something that's still radical, but we can make that the radicand smaller by simplifying. Very similar to this idea. Okay, very similar to that. You also should be able to simplify any variable that I give you in there now. X to the 10th, X to the 6th, X to the 8th. Right now we haven't done any odd power yet, but we'll get to that. This is the method that we would use for that. That's why I kind of preview that information. We should be feeling pretty good about these square roots. However, there are other roots besides square roots, and we're going to talk about those for a while today. Specifically, we're going to talk about cube roots and then move on from there. First, let me tell you what a cube root even looks like. All your roots are going to have a radical. That's that shape like this. That's a shape like that. Every root you ever see is going to have that. However, there's a little space for a number right here in the index portion of our root where a number should go. Now, typically we have a square root, we don't write the number, but you need to know that what's implied here is that when we have a square root, there really is a little number here. It's a 2. We just don't write the 2. That 2 says we have a square root. And it says what we're going to do is every time we see a square, the inverse operation lets us simplify that. So square root and square inverse. That little 2, we never write it. We never see it. It's just implied like, you know how x is actually 1x? Do you ever write the 1? X to the first power is x to the first like that, but we never write the 1. We never write the 2 here either. It's just implied that you know that. Does that make sense? So that right there is a square root because I don't have a number right there. It's implied that that's a 2. If I want to show a different type of root, I just have to put a different number there. So if I put a third root or a cube root, same thing. What does that mean? Let's say the cube root of, and I want you to think of it. Don't say it out loud, just think of it. Think of what a third root would mean. A square root means a number times itself gives you the radicand. What is our radicand here? No, what is our radicand? 8. The number inside the radical is called the radicand. The radicand here is 8 for sure. What we're asking now is instead of a number times itself that's giving you 16, we're asking for a number times itself times itself. Okay, so that's three times. So a number times itself twice, or a number times itself times itself. What number would give you 8? 2, yeah, because 2 times 2 is, times another 2 is, that's what we're asking. What number times itself 3 times will give you the radicand if you have a cube root? So in our case, yeah, that's equal to 2. That's what cube root is. Let's try a few more. Cube root of 27. Just think about it. Just think about it. Don't say it out loud. I want you to think on these things. Cube root of 27 means it's not a square root, right? Hey, by the way, can you even take a square root of 27? Well, you can on the calculator. It's not going to be a whole number, though. Can you take a square root of 8 and get a whole number? Not a square root. Cube roots are different. Cube roots ask one more multiplication in there. So what number times itself 3 times will give you 27? Yeah. Do you think there are more square roots that you can take a square root and get a whole number between 1 and 100, or more cube roots you can take a cube root of and get a whole number between 1 and 100? Look at this. If the first square root I can take and get a whole number is 4, right? I can take a square root of this number and that number and that number. You're thinking in your head 2, 3, 4, 5, aren't you? The first number I can take a cube root of besides 1 is 8. The next number, can you take a cube root of 9? Cube root of a square root, yes. Cube root? How about 10? 11, 12, 13, 14, 15, 16, 17, 18, 19. No. The next one is, look at that. The next one is 27. That's the next number I can, because look at that's 2, that's 3, right? There's no whole number between 2 and 3. So if I can take a cube root of 8, it gives me 2. Cube root of 27 gives me 3. There's nothing between there I can take a cube root of, and it will give me a whole number. Raise your hand if that makes sense to you. So there are going to be less perfect cubes between 1 and 100 than there are perfect squares. There's going to be less perfect fourths to the 4th power than there are perfect cubes or perfect squares. Let's do one more. Let's do the cube root of negative 64. Cube root of negative 64. Let's think about that again. I don't want you to answer out loud on these ones. I want everyone to think on this. Cube root of negative 64. But this asks us, what number times itself 3 times gives you negative 64? And we go, oh, there's a negative inside. No solution, right? No real solution.
One of them's a negative, one of the numbers.
Has to be the same number. Say that one more time.
Negative times negative, positive, positive times negative.
So can we have a negative inside of a cube root?
Yeah.
Yeah, it's different than a square root. Right? A square root says a number times itself. A cube root says a number times itself. Times itself. Is a negative times a negative times a negative equal to a negative? Then these are possible. There's nothing you can't take a cube root of. It's different than a square root. So are negatives possible inside of a cube root? Absolutely. What is this value? What times itself 3 times gives you negative 64? Negative 4. Yeah, it's not positive 4, it's negative 4. Bless you. That was an interesting one. Right. Back to that. It's negative 4 because if you think about it, what's negative 4 times negative 4? Positive 16 times negative 4 again. That's where we're getting that from. So that is possible. Is this possible? Cube root of y to the 3rd power. Cube root of y to the 3rd power. I want you to compare this to what we did over here. What we did over here is every time we saw, please watch up here for a second, every time we saw a square root of x squared, we understood that the square root and the square, those things are eliminating each other because they're inverse operations. And we go, oh, yeah, square root and square, that equals x. Why did that work? Look at the board here real quick. Remember, there's supposed to be a little 2 here. If we match up the power with the root, say that again, if we match up the power with the root, no matter what it is, if we match up those numbers, they are inverse operations. So a square undoes a square root, and a square root undoes a square. A cube undoes a cube root, and a cube root undoes a cube. So what is the answer to this? Exactly. We've matched up the power of the root, right? Those are inverse operations. We're going to get y. So just like we can simplify squares inside square roots, we can simplify cubes inside cube roots. That's kind of cool. And that works for every root we're going to find out in just a little while. Let's try some more. We'll go through a few of these things, and then I'll have you do a couple on your own. We'll talk about nth roots, and that should be about it. We might get to a little bit of graphing. Cube root of 0? Yeah, 0 times 0 times 0, that gives you 0. How about the cube root of negative? How many I can pick from? Let's see if you're really good at this. Just think. Negative 1,000. Don't say it out loud. Cube root of negative 1,000. What times what? Self gives you 1,000. Or in this case, negative 1,000. Very good. Notice how weird, a cube root of negative 1,000 is only up to negative 10 at this point. That's kind of cool. Can you do fractions? Cube root of 1 over 64, that means we're taking the cube root of the numerator and the cube root of the denominator. What's the cube root of the numerator? Cube root of the denominator? Cool. So this is actually equal to 1/4. Interesting, right? It looks a lot bigger than that. It really is. Cube root of x to the 9th. We're going to do the same basic idea that we did for our square roots. Only this time, instead of writing this as something to the second power, I'm going to write this as something to what power, folks? I'm going to try to match up the power with the root. So again, there's two options. I'm going to show you both options until we get down to the section where this is applicable. One way you can do this is write this as x to some power. Don't forget that little 3 there, by the way. You cannot forget that. Otherwise, it changes the cube root into a square root, and we can't have that happen. We're going to want to write this as some x to some power to the 3rd. The reason why we're choosing 3rd, we're trying to match up the power with the root because we know those are inverse operations. What needs to go in there in order to keep that as x to the 9th power? Good, because 3 to the 3rd power, we multiply those. In your head, is it still okay that that's x to the 9th? Don't you have to be okay with that? That's still x to the 9th. We multiply that. Look at power root. Just like with the squares, that simplifies. The other way you could do this, check this out. You could have a cube root. X to the 9th is the same thing as, now I'm not going to write this as x squared times x squared times x squared. Notice if I did that, x squared times x squared times x squared, does a square cancel with a cube root? No, a cube cancels with a cube root. I'm going to write this as many powers of x to the 3 as I can. X to the 3rd, x to the 3rd, that's x to the, let's see, 3, 6, here's 9. That's still x to the 9th. Still x to the 9th. Yes, no? Okay. Every time you see a cube root and a 3rd power, those things are inverse operations. Again, because I can split those roots up, I could write this as the cube root of x to the 3rd times the cube root of x to the 3rd times the cube root of x to the 3rd. Every one of those matches up, just like that example right there. And we would get in either case x to the 3rd. So again, there's two ways we can do that. You okay with that one? So cube root of negative 64 x to the 6. Even though it's negative, it's a cube root, so we can't take the cube root of that. Let's show both ways here again. First way you write this, can you take the cube root of negative 64? Sure, so we're going to leave that alone for now. Negative 64. However, I do need to write this variable as something different. Give me the first option in writing that variable. How can I write x to the 6 so that I can simplify it with a cube root? X squared first or x cubed? You have two options, right? One of them is for a square root and one of them is for a cube root. You're either going to write this as x to the 2nd to the 3rd or x to the 3rd to the 2nd. Which one's going to work here? Perfect. X to the 2nd to the 3rd. Why? Because we're trying to match up the cube with a cube root. That's what we're doing. Notice how this power has to match that in order to simplify. Cube root of negative 64, we already know that's negative 4. Cube root of x squared to the 3rd. That 3rd and the cube root, those simplify out, we get x squared. The other way that you could do this, negative 64, and you could write this instead as x to the 3rd times x to the 3rd. Do you see that those x to the 3rds are going to simplify? Which way do you like better, the first way or the second way? Which do you think? Like the second way? First way works great for even, doesn't work so good for odd. You can't do that. So hopefully you get comfortable. If you're comfortable with this one, great. I need you to be comfortable with this one as well later on. In either case, those simplify out. I still take the cube root of negative 64. I have two x's that I was able to simplify out of that radical. Negative 4x squared is our answer. I'd like you to try a few of these on your own. By the way, there's not a whole lot of numbers I can give you right now that you can find the cube root of, because if you think about the first 5 perfect cubes, well, there's 1, then there's 8, there's 27, 64, 125. But that's the first 5 perfect cubes. So you can only take the cube root of those 5 numbers that are between 1 and 200. Okay, so first example, we have cube root of 27 over 64. We're going to take the cube root of the numerator and the denominator. Cube root of 27 is, these are going to be very familiar numbers after a while, because again, there's only 5 of them I can have you do. 1, 8, 27, 64, 125. That's it. And if it's not one of those numbers, you can't take the cube root of it and get a whole number out of it. So here we go, yeah. 3 over 3/4 for sure. Cube root of x to the 12th, you're going to do this one of 2 ways. And either way, first way you do something to the, we want 3rd power. We want to match up the power of the root. What number has to go there? We would get x to the 4th. If you do it the other way, you're going to get the same answer. You have to write x to the 3rd, x to the 3rd, x to the 3rd, x to the 3rd. That's 4 times. We simplify each one of them and get x to the 4th power. Here, the cube root of negative 8. What's the cube root of negative 8? Good. And the cube root of x to the 3rd, those simplify, we get just an x out of that. But you're going to have to be okay with these cube roots. Good deal. Guys on the right hand side? Let's move it up one more time. We're not going to talk about square roots now. We're going to talk about cube roots now. We're talking about any root that I want. And we say any root that we want is an nth root. What's the n doing there? N stands for any integer number, or any whole number that you want. One, oh no, sorry, not one, you can't take out one root. Square, 2, 3, 4, 5, 6, 7, 8, 9, 10, forever and ever and ever. Whatever type of root that I want to talk about. Here's how every root looks. We know we have a radical, and we know we put a little number up front, that index, that indices right there, is typically, if I don't write anything, what's that index? 2, good or x squared, a square root. If I put a 3, it's a cube root. If I put a 4, it's a fourth root. 5, it's a fifth root. Whatever number I have there, it's that type of root. That's how we're getting the nth root. Second root, third root, fourth, fifth, sixth, that type of root. For instance, can we think about what the fourth root of 16 means? What's the fourth root of 16 mean that you're looking for? We know square root is a number times itself, right? Cube root is a number times itself times itself. What's the fourth root mean? Again, yeah, that's all it means. Same idea. Can you think of a number times itself? 4 times it gives you 16? Yeah. That's all an nth root is. It's whatever I give you. It's the number times itself that many times it gives you the radicand. By the way, do you think that you're going to be able to have a negative inside of a fourth root?
No.
Negative times a negative times a negative times a negative gives you a Do you think you're going to have a negative inside any even root?
No.
That's impossible. If you have an even root, that means a number times itself an even number of times. So 2 or 4 or 6 or 8 times. If you have the negative that many times, you're going to get a positive number. There's no way to get a negative number. How about inside of a fifth root? Is it okay to have a negative inside of a fifth root?
Yeah.
You have the extra time, right? The extra time where it doesn't match up evenly, 2 by 2, is going to make your answer negative. Or potentially you could get a negative inside of that root. Is it okay to have a negative inside any odd powered root?
Yeah.
For sure, that's okay. That's okay. Because you have the extra negative tacked on, that's going to change your answer to negative. How about the fifth root of negative 32? What do you think on that one? Good, because negative 2 times negative 2 5 times is going to give you negative 32. Again, is this possible? We have a negative outside of square, is that okay? That's how much? What's our n here, by the way? What's our n? Good, okay. And that one is, why no real solution? Yeah, it's an even root. That's right. We can't have a negative times a negative times a negative times a negative and still get a negative. That doesn't work. So we're not going to write just no solution. It's no real solution. Actually, not. Okay. Don't go that far. How about that one? Can we do that? Can you deal with variables inside of any type of root? Sure, okay. What is the fifth root of 32? How about the fifth root of x to the fifth? Can you do that? How much do you think it is? Exactly. The same principles apply. So fifth root, fifth power, those things are also inverse. No matter what your n is, if you have that power inside of your radical, then you're also going to be able to simplify that. So that's just 2x. There's 2x. So a couple notes that we just learned. If n is even, you cannot have a negative as part of your radicand or inside the radical. If n is odd, though, the last thing we're going to talk about, we won't get into the graphing today. I just want to show you one more thing. The graphing actually is just a refresher on a previous topic that we've covered. The last thing I want to show you, we're going to talk about roots of the form nth roots of something to the nth power, where the nth power and the nth root match up. You see, there's one little, I don't want to say like a catch, like this is trying to trick you or something, but there's one idea that you need to be aware of when talking about these type of roots. And here's the idea. Let's say that I have a square root of -5 squared, and I have a cube root of -2 cubed. Here's the issue. I need you to know why this is kind of a problem for us in one case and not a problem in another case. Watch on the board here real quick, okay? If you understand all this stuff, great, that's awesome. I need you to get this little point down. Firstly, you are okay, right, that whenever a power matched the root, we could just cross it out. Understand? So in this case, I want you to look at the board. In this case, we should be able just to say, oh, that's a square root, that's a square. I should be able to cross that out, and we should be able to get -5 out of that. Do you understand that? We should be able to do that if that's true. In this case, we should be able to cross out the third power and the third root and get -2 out of that. Are you with me on this? That's exactly what we just did. However, I need you to notice something. If you really do the order of operations and go, oh, well, this is, what's -5 squared, actually? 25. That's a square root of 25. What's the square root of 25, folks? Now, we know that one's true, right? Because we just did it. Are these things equal?
No.
That is, why? Should it just do that? Why does that happen? On this case, though, check it out. Check it out. If we have a cube, if we have a -2 to the cube, what's -2 cubed?
6.
-8, sure. What's the cube root of -8? Not just 2, right? -2 times -2 times -2. That's -2. Are you with me on this, folks? These things, cool, those do work out the way we want it to. Happy things, right? This one, what happened here? This one's fine, right? This one we can just cross it out. This one we couldn't. And Lily's over there saying, yes, one's even, one's odd. Yeah, of course. That's actually the reason why. If you have an even power, what it does is it says inside your root, it says, oh, I'm going to make whatever you have positive, right? No matter what. The negative inside of a third power or a fifth power or an odd power is saying, I'm going to keep that negative. That's fine. So what we get out of this thing is that we can't just cross this out. How can I change, by the way, a negative, this one, to match up to what we actually know? How do I change this into this? What do I do to change this into this? Something we've already used in this class in the previous section, in section 9.3 and 9.2. What changes to positive to a negative, no matter what? We could multiply. I don't want to multiply by anything, though. So another option that is a good idea. Absolute value. Here's what we need to know about this. When you take an even root over even power, what we get out of this is not just that we can cross this out and get -5. What we do is we cross this out, sure, but what that actually equals is the absolute value of -5. What's the absolute value of -5? That would make this true. Do you see that? That would make this true. Now we have something that's equal, and we get another smiley face. That's for some reason looks like a weird smiley face to me, kind of freaky. It's me. Here's what we're just learning right now. Last thing we'll probably write down here. What we're understanding is that if n is even, like it is here, what this is going to equal is you're still going to be able to cross things out. An nth root still matches with the nth power. You're seeing that, right? They still match up. However, if n is even, what you're getting is not just a, we're getting the absolute value of a. Getting the absolute value of a, not just a. But because we know that here, our a is -5, we're not just getting -5, we need to be getting +5. We're going to take the absolute value of that. If n is odd, though, it doesn't matter. N is odd, it doesn't matter. I want to show you a couple examples in our last minute here just to make sure that you guys really see this. By the way, these don't take a whole lot of work. You're not even going to work on them. You're just going to cross stuff out and understand that one of them's going to have an absolute value and one of them's not. That's basically it. If it's even, it has absolute value around it. If it's odd, it doesn't. So let's do 6 through x to the 6th. Firstly, does the power match the root, ladies and gentlemen? Yeah. So I'm still going to be able to cross these things out. You just have to understand when I'm going to have an absolute value. When I'm not. Do I have an absolute value here? If it's even, if n is even, I'm going to have an absolute value. Is n even?
Yes.
So am I going to have an absolute value or not?
Yes.
What the absolute value means is that when you have an even powers make everything positive. What else makes everything positive? Absolute value. So you cross things out as long as you have the absolute value. That's what even does. Odd doesn't make everything positive. It leaves negatives negative. Therefore, when I have an odd n, it doesn't matter. You can write the n itself. So here's one. How about this one? Cube root of -3 in parentheses cube. Am I going to have an absolute value or not? What's the n? What's the n here? There's only one number to pick from, right? They're all 3. Just say 3. Yeah, that's your n, right? N's 3. It's an odd. What odds don't make everything positive. Therefore, we don't need an absolute value. How about that one? Does the power match the root? Do we need an absolute value or not?
Yes.
So there's no work here, folks. If it matches up, you know it's going to simplify. You just have to know whether you need an absolute value or not. What do you think on that one? Absolute value or not? Absolutely not. Because it's odd, you don't need absolute value. But you have to feel pretty good about this stuff. Okay, we have a couple more ideas on this, maybe about 5 minutes extra. We'll do this after our test on Wednesday. So the last thing we've got to do, we've got to graph some of these radicals. Again, I want to refresh your memory on how to graph just the square root of x. But then I also want to graph the cube root of x. And we're going to do this with a table, just to be thorough, because we really don't know how this one looks. Let me change that to a G. Now, when we're graphing tables, we typically use just 3 points for lines. However, with these things, we're going to use like 4 points, 4 to 5 points, to make sure that we're really thorough and understand what's going on. So let's go ahead and pick out some points for the square root of x. What points am I going to want to use here? What's one point I always use?
0.
Definitely 1, 0. Put that right there. Another point I might want to check out is 1, because it's easy to plug in. So let's find out what happens at 1. How about 2? Am I going to want to plug in the number 2? Can you find the square root of 2? You can. You can on the calculator. But if you just go square root of 2, you go 1.41? Yeah, it's 1.41. But you're not going to probably know that. You definitely don't want to graph it on the graph, do you? What number do you know the square root of? Let's pick 4. And give me one more. Let's do 9, 4, 1, 0. Let's pick out some negatives, negative numbers. What do you want to pick for a negative number on the square root of x? 1. Negative 1? Okay, we'll try negative 1. You know, let me give you some more space here so you can see those numbers a little better too. We have 9, 4, 1, 0, negative 1. That'll be good enough for us. Let's see, we're taking 9, we're going to plug this in. What's the square root of 9, ladies and gentlemen? Okay, so that gives me a point, 9, 3. 4, what's the square root of 4?
2.
That gives me a point, 4, 2. How about square root of 1? Square root of 0? Good, that is possible. 0, square root of negative 1. So that's why on our graph, well, square root of 1, that doesn't even happen. That's why on our graph, when we graph this thing, there's nothing on this side of our graph, because you can't even plug in a negative number. You can't plug in a negative number to a square root, can you?
No.
You have no real solution. So when we graph these points, we'll start from the bottom up. I know 0, 0 is there. I know 1, 1 was there. But then we have to go all the way over to 4 to get a 2. So that's, notice that this is x comma y. So 1, 2, 3, 4, comma 2. That's right here. And then to get up to 3, I have to go all the way over to 9. So 9, 3 is my last point. That's why we got this funny looking curve. It's a half of a parabola on its side. That's why it kind of looked like a square root actually. That's our graph. You guys remember that graph? It's from a while back. How many will do remember that? Feel okay with it? See where these points are coming from? And most importantly, do you understand why we have no graph on this side of the y-axis? Do you all understand that? Can't plug in negatives, that means you're not going to get anything out over here on this section. Now let's see what happens with our cube root of x. I still want to plug in 0. I definitely want to find out what happens there. And I want to see what happens in 1. Now, do I want to see what happens at 4? Can you take the cube root of 4? What can you take the cube root of? Not 3. Not 9.
27.
That's something that said it 3 times now. I could do 27. You're right, I could do 27. But you know what? I don't want to put 27 in hash marks because I'm lazy and I don't want to draw a graph this big. So yeah, I could check 0 because 0 is nice. I can check 1 because 1's nice. 2, what's the cube root of 2? You go, I don't know. What's the cube root of 3? I don't know. Cube root of 4? I don't know. I take the square root of that. Cube root of 5, no. 6, no. 7, no. 8, yes. 9, no. 10, no. The next one would be 27. So numbers you can take the cube root of are the same numbers we've actually only been taking the cube root of, which are 0, 1, 8, 27, 64, 125, 216. All right, those are the only ones between there and 200, and, well, 300 something. So 343 is the next one for 7 cubes. So you don't want to do those, right? There's only a few of them. So the only ones we can pick are 0, 1, or 8. Maybe 27 if you really want to draw a large graph. You don't want it. Now let's try some negatives here. Let's try -1 again. Let's see if that works. Is -1 going to work in this particular problem? Is there a difference between a cube root and a square root? Yeah. Cube root has one extra time. A negative and a negative and a negative could potentially give you a negative, couldn't it? So that, for this reason, we can actually plug in negatives into our graph. We couldn't here because a negative times a negative that only 2 times won't give you a negative. They'll always give you a positive. But if we're doing 3 times to equal the radicand. So negative, negative, negative potentially give you a negative. Will always actually. And then we'll try -8. So let's do this together. If I plug in 8, what's the cube root of 8, ladies and gentlemen? 2. Okay. That gives me a point. Cube root of 1. We're asking here again, remember we're saying what times itself 3 times is giving us the 8. This is the cube root of 8. What times itself 3 times is giving you the 8? Well, that's 2. Here it's going to be 1. How about 0? What's the cube root of 0? For sure. What's the cube? Oh, -1. The cube root of -1 asks what times itself 3 times gives you the radicand of -1. Yeah, let's think about that. -1 times -1, that's 1. Times -1 gives you -1 again. So that means that our cube root of -1 is -1. And lastly, cube root of -8, everybody? Well, we've got some points. Let's see what this looks like. Notice that our points do come x, comma, y, just like always. So we have to go over to 8 on our x-axis. Also, am I going to have a piece of my graph over on the left-hand side in this case?
Yes.
Yeah, this is different over here. Here I couldn't plug in negatives. Here I could. Now I'm doing something a little bit here that's going to be a little bit off, and I want you to see what I'm doing. I'm doing it just so you can see the graph a little bit better. Do you notice how my hash marks here are a little bit bigger than my hash marks here? Just expand my graph a little bit this way. This is actually supposed to be a little bit flatter than what I'm going to draw. Are you with me on that? So I'm biasing the graph vertically a little bit, just so we're able to see it. So let's go ahead and plot these points. I'm going to work from the middle. I have 0, 0. I have 1, 1. That's here. I also have -1, -1. Is -1, -1 up here or down here? Okay. Then I have 8, 2. 8, 2 says 8, 2. That's over here. And I have -8, -2. -8, -2. That's a weird looking graph. Can you picture in your head what it's doing? Picture what it's doing. It looks similar to this, doesn't it? For part of it. It looks similar to this for the other part, except it's rotated 180 degrees. So, all the way around. This right here, this graph, it's like an S curve. It does do that. Actually, it doesn't. It's actually flatter than this. It's flatter than that graph. So I am lying a little bit. I've expanded this just so you can see the curvature of this. But this should be a little bit flatter than this one. It's more radical, because notice what you're doing. Here to get out the value of 2, you'll have to plug in 4. Here to get the value of 2, you have to plug in 8. That's going to squeeze it down closer to the x-axis. But then this side looks exactly the same, only going below the x-axis. It's kind of like a reflection. It's really a rotation. But it does that curve. It's a nice S curve. That's the cube root function. That's the cube. One more thing I want to talk about here. Let's say that, I'm not going to graph all these, it's just a ton of them, but let's say we wanted to graph a fourth root. A fourth root. Can you plug in a negative number into a fourth root?
No.
Can you plug it into a fifth root?
Yes.
How about a sixth root?
No.
Seventh root? So, what will every even root look like? This one or this one? What do you think? The square root or the cube root? Square root. Every even type of root, fourth root, sixth root, eighth root, 10th root, will look similar to this. It'll have this general shape and only be one-sided because you can't plug in negatives. However, the higher you go up in your root, the flatter this will get. Okay? In order to get 2 out of a fourth root, you'd have to plug in 16. All the way over here. Okay, just to get the value of 2. It's going to flatten that out. It'll really flatten it. Every odd power root, 3, 5, 7, 9, will look something like this. It'll have this negative version as well, because you can plug in negatives to it. So it'll be some sort of an S curve. Now, the only thing we got to talk about is that the shifting still works. On your homework, it's going to ask you to make tables for all this stuff. I really don't care about that. If you want to make tables, great. But do you understand the shapes of these guys? If you understand the shapes, you can manipulate them by shifting them around. Now, for a fifth root or a fourth root, you might want to draw a table once, just to kind of see the values and how it looks. Okay, draw it one time, and then if it asks you to shift it, go ahead and shift it. So since we just graphed some of those things on your test, if I ask you to do f of x equals square root of x plus 1, like this, where it's inside of the radical, you should be able to tell me what type of a shift that is. Is that a shift up, down, left, or right? Firstly, let's determine whether it's a vertical or a horizontal shift. Now you tell me, is this plus 1 within the function or after the function? It's within. So is it a horizontal or a vertical shift? Remember, after would have been up or down. Okay. This is within the square root. That's why this little tail here is covering that plus 1. This is within the square root. So this is going to be a shift either left or right. Remember, my original graph looks like this. My original graph looks like that. What did the plus 1 do if it's inside of your function? Was that a shift to the right or a shift to the left? Which one was that? Left. That's right. So this is a shift to the left. If it's inside, it was horizontal, and it was kind of backwards of what your head wanted to say. This was left 1. So here we say, oh, okay, let's move our vertex one spot, redraw our graph. We can shift these graphs around, just like we did before. Are you okay with this? Okay, let's try one more. Let's do g of x. Cube root of x plus 2. Cube root of x plus 2. Of course, you need to know what the shape of the graph looks like, which is why I'm going to have you draw at least one graph using a table for like a fourth root and fifth root. But then after that, you can just shift them around. That's fine. What's this graph look like? Does it look exactly like this? No. That other side to it. So the original one would look like that. Something like that. Can you tell me what this plus 2 does? Is the plus 2 within the function or after the function? So is it a horizontal shift or a vertical shift? Definitely. And it's going to go up or down. So this says you're going to take your graph, just move it up 2 spots. If we move it up 2 spots, we're going to redraw the same exact thing. And that's my new function. We can shift these things all over the place. We can do combinations as well. We can do something within the function and something after the function. We could even reflect it with a negative up front that would flip these things upside down. If you flip this upside down, notice you're going to get a Z curve instead of an S curve. You with me on this, ladies and gentlemen? How many understood what we talked about today? Good. Well, that wraps up our section 10.1.
I always travel with a